Mikko, without further ado, introduce yourself and tell us what's up. What do you got?
Yeah. Hey everyone. Mikko, AB6RF. And Rob, you absolutely well. Actually, technically, it was last year when I tapped on your shoulder that hey, why don't we have a presentation about this topic? And I don't know who's there at Carberley in person, but if Uncle Frank is, we should kind of thank Uncle Frank for planting the seed for this presentation. This all started from a quick little chat I had with Frank there at the parking lot outside of the Marriott Hotel when we were setting up the when we were setting up for Pacificon last October. And I talked with Frank about this topic briefly and thought, wait, this is actually pretty interesting, and I wonder if other people would be interested in this too, and that's where this whole thing started. So that let's get started with the presentation. So I need to share my screen with all of you. Share screen. All right. Doug, you need to allow me to screen share. It says host disabled participant screen sharing. Is there something our host can do to enable that?
I think I have it. Mikko, try now.
Let's try again. There we go. Okay, I'm gonna share that. Let's see how this works. All right. And I can probably.
We see it.
Good Perfect. Job. Let me shrink that a little bit on my screen so I can see other stuff still.
It looks good here.
Perfect. Okay, where's the presentation? Sorry about the fumble. It'll get better once we get going. As soon as I just get my screen set up here. Okay, I was hoping to see at the same time what you guys are seeing. Looks like I can't do that. It's okay. I'll just go. I'll just kind of fly blind. I see my own slides, of course, but I can't see exactly what you are seeing. So that's all right. So so the title for this evening's presentation: HF propagation with a twist, and you'll see what the twist is. We'll talk a little bit about electromagnetic waves. That's the whole basis of whole thing. Circular polarization, ionograms, ionosphere, NVIS or NEVIS or however you want to pronounce that. We'll touch upon on all these interesting topics, and you'll see by the end how all this kind of ties together really neatly. It seems like a basket of disconnected topics. Turns out it's not that. All right, so we'll start just by looking at the electromagnetic waves, how to make the electromagnetic waves, how do antennas radiate, and then about the radiation specifically, we'll kind of remind ourselves about the polarization. There's the linear polarization and circular polarization. We'll look at those and kind of interesting aspects of each. Okay. How to make electromagnetic waves. That's sort of where this whole fun stuff starts. So first here's my illustration. What you see there at the bottom, that is supposed to be a dipole antenna. It's kind of short and fat, but you can still make out how that's a dipole. And then you have a DC source, a voltage source connected to that dipole. So what happens in this situation? You connect a DC source, even say like really high voltage, more than just a battery, you connect that to dipole antenna. Are you making electromagnetic waves? Is that thing radiating? It does not. So what happens in this situation is the little blueberries there with the minus signs, those are supposed to be the electrons. So you know what makes a conductor, starting from very basics. Conductor is a material where the electrons or other charged particles are free to move when voltage is applied. So here we have this copper wire. There's a lot of free electrons in there. They are free to move. You connect the battery. Initially, there's a lot of motion. All the electrons, what they do is all the free electrons, they kind of bunch up there at one end of the dipole, as far away as possible from the negative terminal of the battery. But after that initial rush of electrons, then nothing happens. It's a very static situation. And that's why this thing does not radiate
Thanks.
RF or electromagnetic waves. So here, this is what's required to create the electromagnetic waves to generate RF. You have to be accelerating those electrons. So what you need to do is you need to connect an AC source, alternating current source, to your dipole antenna, and that's the illustration here. So now that AC source in the middle, in real terms, the AC source is your transmitter that puts out RF. You know, RF is AC. It's just very high frequency AC. And what your transmitter does, what really happens between the transmitter and the antenna is the transmitter is yanking those electrons back and forth, essentially left and right. So they are accelerating all the time, back and forth, back and forth. And that back and forth acceleration creates the EM waves. That's what's required. That's why the antenna radiates, and that's what's happening there. So it's the accelerating charged particles, most often electrons, that creates the EM waves. And sort of the interesting part is that electrons, like you might remember from the high school physics, electrons have almost no mass at all, but still it takes real power. I mean, our transmitters, 50 watts, 100 watts on HF, that's real power. Real energy goes into the antenna. And why that is as the electrons, while they are accelerating back and forth, while they do that and while they generate those EM waves, the EM waves sort of rob energy from the moving electrons, that they push back on that electron movement. This is like real stuff. The electrons actually move there, and the EM wave pushes back on that movement. And to overcome that pushback, so to speak, that takes real power. That's where the power goes from your transmitter, is into accelerating those electrons that are being pushed back by the EM wave. So that's why it takes power to generate EM waves. Does things sort of make sense so far?
Yeah, sounds good.
Yeah,
Well,
yeah.
I've heard of this weird absorber theory that says they can only accelerate if there's going to be an electron somewhere else for them to move, and that the power can go into the fact that they're going to move some other charges somewhere else. But I shouldn't get into that with you right now.
Yeah. There's a lot of details. On a high level, the important thing is that you have to accelerate the charged particles back and forth, and that generates the EM waves. And talking about the frequencies there, so typical 80 megahertz frequency, like say 3.8 megahertz, you are physically moving the electrons back and forth 3.8 million times a second. So this is all real stuff. There's real things. There's real particles moving back and forth inside that copper wire, and that's how we make the EM waves.
A question that I'm not asking you to answer, but putting out there: if you have a cyclotron and the electron is constantly accelerating in the same direction, do you get a 0 hertz radiation?
Well, in a cyclotron, there's still acceleration, right? They are on a circular orbit, so there's acceleration because they are accelerated towards the center of the cyclotron.
Right.
So what's the frequency?
Exactly.
I don't know. I haven't used one of those transmitters ever. So.
Back to your talk.
Cool. Thank you. All right. So this is how we make EM waves, electromagnetic waves. Then next stop on this path is the polarization of those electromagnetic waves. So carrying on from the previous page, we have those back and forth moving electrons inside that, copper wire dipole. The dipole exists in one plane, so the electrons are moving back and forth in one plane, and that's going to be our the plane of the electrical field of the EM wave. So EM wave has two components. There's the electrical field and there's magnetic field. In the animation here in the bottom, hopefully it plays for all of you. You see the blue E arrow, and there's the red B arrow. So in this example here, the electrical field E is going up and down, and there's the perpendicular magnetic field that's always there coupled with the electrical field. It's in this example in the horizontal plane. So we have those accelerating particles. They are in one plane. They generate a plane wave where, like, electrical field, this case vertical, and you see how the electrical field, its magnitude oscillates, back and forth in sinusoidal fashion between 0 and then positive and negative peak values. So the important thing is that the magnitude of the electrical field and the magnetic field constantly changes, but the plane of it stays the same. Next thing, here's this kind of oddball thing, circular polarization. It's kind of interesting. So on a very sort of simple conceptual level, I think we've all seen and read about the circular polarization, often used, for example, for satellite communication. But really, like, looking a little bit deeper, what does it mean? How does the circular polarized electromagnetic wave look like? So what it looks like is that there's one sort of representation there on this page. Interesting thing here is that the magnitude of the electrical field, it's not changing now. Like here on the previous page, see the magnitude of the E field keeps constantly changing. In circular polarized field, it doesn't. The magnitude is constant, but it's rotating around, and it rotates once 360 degrees. It rotates one rotation, and exactly one rotation for every RF cycle. So 3.8 megahertz, again as an example, the electrical field turns 380 degrees, one turn, 3.8 million times a second. So while theoretically you could generate a circular polarized electromagnetic wave or signal by rotating that dipole real fast, it's completely impractical, because even for such a low frequency as 80 meters, you'd have to spin that dipole 3.8 million revolutions per second. So you don't do that. The EM wave, the circular polarized EM wave, it can of course rotate both ways, clockwise and counterclockwise, or right hand circular polarization and left hand circular polarization. So yeah, instead of spinning that dipole crazy fast, of course the practical way, one example is the turnstile antenna there, where you have two perpendicular dipoles and you're feeding them 1/4 wave out of phase, and that's how you generate the circularly polarized electromagnetic wave. Let's see if this one animation works here. I hope you guys can see that. This is really cool animation that really like shows the circularly polarized EM wave. Here there's the green arrow and yellow arrow. Doesn't matter which ones, we'd say green is the electrical component and yellow is the magnetic field component. Same way as with the linear polarization, they are always at 90 degrees from each other. So they are always, 90 degrees out of phase. But they both rotate exactly one rotation for each RF cycle at constant magnitude. So I really like this animation for sort of illustrating how the circular polarized wave really looks like there in space.
Because
All right.
the previous slide, the animation that you had, the linear polarization,
Here.
shouldn't, or did I have it long all these years? Shouldn't the E and the M be 90 degrees out of phase in time too?
This is so sort of the side topic of this presentation was something along the lines of let's kind of rectify some common misconceptions along the way of the presentation. That is probably the first one of those. You've
Great.
had it wrong all these years. In the EM wave, the magnetic and the electrical fields, in time, they are in phase. They are orthogonal in space, but the phase is the same.
Well, that puzzles me because I thought that the one would be proportional to the acceleration of the other, and the acceleration should be 90 degrees out of phase, should it not? Or is the acceleration in phase? Is it velocity that's 90 out and acceleration's another 90 from that, so they're in phase?
I can't even answer that, like why is it? But in the linear polarized wave, they are actually in phase. I think we often think about like LC resonators, like tank circuit or any LC resonator, where the energy does, oscillate between it's all in the magnetic field and or in the electrical field in the capacitor. So there, yes, absolutely, they are completely out of phase. But in the EM wave, the two fields are actually in phase.
Because I did think that it was velocity, as I think about it, that it was motion of charges that creates the magnetic field magnitude. And if that were the case, they ought to be 90 degrees out of phase. So I'm quite puzzled, and I'd love to learn more about this.
Yeah,
but I don't want to stop your talk.
And I can share. So on the topic of like learning more about it, and I have the note there later on in the January issue, just this most recent January 2022 QST issue. There was a really good article. The article was specifically about the ionograms, and we'll actually take a look at those later. We'll talk about the ionograms. There was an ionogram article in the QST, the January issue. The author of that article, he's written a book, just turns out. It's here. There, I can't see what you are seeing. Propagation and Radio Science by KL7AJ. There. If you want to learn more about anything we are talking about tonight, it's in here. And if you want to learn even more, my wife can bring the real Bible from downstairs, the black book on the coffee table. So yeah, really, no joke. This is an excellent book. It's fun reading too. He's really good author. It's fun reading his stuff.
Thank you.
Yeah.
Thank you.
So anyways, there was the linear polarization. Oh, here comes the real. Here comes the real. if the amateur hour version doesn't cut it for you, then there's this. This is the real truth. Okay, circular polarization, constant magnitude, rotates one rotation per each RF cycle.
Question,
Sorry.
what was the title of the second book? We just looked at it briefly.
Oh yeah. Title is, it's kind of simple title. Ionospheric radio. Ionospheric radio, yeah. There we go. Kenneth Davies, I think it reads. Again, I can't quite see what
Thank
you
you.
guys. There we go.
Yeah.
Kenneth Davies ionospheric radio. It's out of print. You can't find this anywhere. Sorry to say. It's, or maybe you can. Like I can't say you can't find it anywhere, but it's out of print. It's kind of hard to find book. I can borrow mine if someone's really interested. I can borrow this here and you can take a look. Okay, cross polarization between antennas, or sort of cross polarization between the signal you are interested in and the antenna. Like we all know, polarization mismatch between the signal you are, say, trying to receive and between the polarization of the antenna you have causes signal loss. There's always some amount of signal loss. We are pretty familiar with the few typical examples. When we're trying to get into N6 NFI repeater, you better be using a vertical antenna because the repeater antenna is vertical. You can get in there with the horizontal beam as long as you have enough gain, you have enough signal, but you're losing quite a bit of signal because of that cross polarization mismatch. Same thing the other way around. If you're trying to get into the 2-meter Bozo's net that's on sideband, all those guys are using horizontal antennas. If you're trying to get in there with the vertical antenna, maybe you'll be successful, maybe not. You're losing a lot of signal because of that cross polarization, like real polarization mismatch between everyone else's signal and your signal. Good example of the cross polarization and how to deal with that are the current crop of the low Earth orbit ham satellites. Some years back, a lot of the ham satellites actually used circularly polarized antennas. Nowadays, they don't. Almost, I'd say pretty much all of them use just a monopole antenna, which is a linearly polarized antenna. Monopole, think of it as, a vertical antenna, quarter wave vertical. That's what pretty much all the modern satellites use. But the orientation of the satellite is random. So from our view, the satellite is, or its antenna, it's not sitting there vertically. It's generating a linear polarized signal, but we don't know what orientation it's at. It's any random orientation. So that's why the satellite guys, everyone's using still circular polarized antennas so that you can still pick up that incoming linear polarized signal at the random angle. So here's the table at the bottom. Of course, if you have two linear polarized, or you have a linear polarized signal, you're receiving that with the correctly polarized antenna, there's no loss. Perfect situation. That's the gold standard. When you are 90 degrees off, you are trying to get into that repeater with the horizontal antenna, there's a pretty large signal loss. I'd say few S units. So, quite a few dBs. If you're doing the wrong thing between left hand and right hand circular polarizations, that gives you a large loss. So several S units, you lose a lot of signal there. And then the last row is that satellite example I just mentioned. So the signal from the satellite, it's polarized at some random angle. We'll pick it up with the circular antenna, either crossed beam or a helical antenna. We lose 3 dB. It's not ideal, but we never lose more than 3 dB because we aren't ever in that 90-degree cross-polarized, really bad situation. So we're going to give up 3 dB and get the benefit that we are never in a really bad situation. We avoid those really deep signal fades. Sort of the same thing, just like driving the point one more time. So circular polarization to linear polarization, polarized antenna. So the circular polarized antenna, it doesn't really care at all at what angle the incoming linear polarized signal is. So there on the left, there's the helical antenna. If it's talking to a dipole, it doesn't matter in what orientation the dipole is. Vertical, horizontal, slant, 45, it's all the same. You always lose 3 dB, but you don't lose more than 3 dB. So that's the good part there. All right.
Yeah,
Next.
point about that, Mikko.
Yeah,
Yeah, but you do lose if you're off the axis, or not pointing towards the satellite.
absolutely. Yes. That's sort of just normal antenna gain. So if you have more antenna gain, you get more signal. You also lose gain if you're pointing the wrong direction. So yeah, that's your gain is just dropping off. So that's absolutely true. So that there's that part too, and then there's the other aspect. Actually, if you are really, if you take my drawing here, like really sort of take a literal sort of interpretation of this, the dipole antenna marked with H, it's showing horizontal dipole. The way it's drawn here, that antenna wouldn't actually pick up anything from the helix because it's the end of the dipole, pointing to the incoming signal. So then there's that. There's like, which way are you pointing, and is your antenna even oriented in such a way that it can pick up the signal? So that would be the extreme case where that dipole wouldn't pick up anything from a signal that's coming straight from the left. But the point is that the orientation of that dipole doesn't matter, whether it's horizontal, vertical, or slanted in any random way, relative to the incoming circular polarized signal. Cool. So then we're jumping into sort of the next section of the presentation, ionosphere. Same thing, just like earlier. Hopefully we'll rectify a couple sort of maybe common misconceptions. Certainly misconceptions I had. We'll look at the different regions of the ionosphere, their height, physically how high up they are, and that of course then relates very closely to the skip distance. How far can you have a contact with just one skip, or do you need multiple skips? There. So this is probably something all of you already know from the past. So not much new info on this page. I thought just a quick refresh on the regions of the ionosphere or regions of ionization would be a sort of good start here. So the lowest region of the ionosphere, the D region, and by the way, I'm using the word region. Often we talk about ionospheric layers. I'm gonna using them interchangeably. Region, layer, same difference. But if we talk about layers, that might again paint a little bit incorrect sort of picture of how the ionosphere is. When I think about layers, I think like layers in a cake, which are very sort of distinct, and there's this layer, and then there's nothing in between, and there's the next layer. That's not how ionosphere is. It's just sort of these fuzzy regions of different kind of ions and different ionization levels. So it's more of a region. So I'm going to use the word region a little bit more than the layer, but kind of the same thing. So anyways, during the daytime, the lowest layer or region of ionosphere is the D region. D layer doesn't do anything good for us ham radio guys or gals. It only absorbs medium waves. It absorbs the low end of the HF frequencies. Good thing is it disappears pretty much as soon as the sun goes down. D region disappears completely during the night pretty quickly. So that's when the HF propagation is at its best. Next region up is the E region or E layer. A little bit more useful. It provides the nighttime skip on medium waves, and also often on the low end of the HF frequencies. That's E layer provides that skip. And then there's the ES. We've heard about the ES propagation. I want to remind everyone that ES is not really a different layer. It's just a different propagation phenomena within the E layer. So ES is not a different layer. It's the same old E layer. It's just when the ES propagation happens, there are these really high density ion clouds forming within the E layer, and those give us the ES propagation. The ES is like you guys know, is not very well understood, and what's not well understood is what exactly creates those really high density ion clouds that then reflect the RF signal. Typically the E layer density is not that high. There are these really like concentrated ion clouds, and what's really creating those, what makes them happen, that's not very well understood by now. And then the topmost layer of ionosphere, the F region, that's the most useful, highest electron density up there. That's what gives us the good HF propagation when we have it, like we just had on 10 meters. Very true, 10 meters was open. That was all F region, reflecting the signal back down to South America. The blue text there at the bottom, kind of useless, trivia information, but I thought it was really interesting when I stumbled onto this one. So the volume, the like sheer volume of ionosphere is huge. Ionosphere is much bigger than atmosphere, but it's almost nothing up there. It's really low density gas or ions there. It's almost empty. There's almost nothing up there. Even with that huge volume, the total weight, and I didn't measure this. I reached just researched the info and found this. It's been estimated that the total mass of the entire ionosphere over the whole Earth, the total mass is only 1 ton. And you compare that to the weight of the atmosphere, 5.5 quadrillion tons. So that's 55 and 14 zeros. That's the weight of the entire atmosphere. And you compare that to the entire weight of the ionosphere, which is just 1 ton. You kind of see how the ionosphere, there's almost nothing there. It's super empty. It's kind of interesting. Here, so this was one of those I don't know, maybe common misconceptions or not points. The picture in the left is something you often see in textbooks and even in ham radio study guides. That's kind of what the picture looks where they introduce us to ionosphere and ionospheric propagation. You see the signal there, it goes way up, reflects from the ionosphere, comes back to Earth, and in couple of skips you get to the other side of the Earth. That's sort of the typical textbook picture. It doesn't look like that. That is very incorrect. It kind of conveys the very rough idea, but the geometry, the scale is completely wrong, and it kind of gives a wrong idea of what's going on. The picture on the right with the blue Earth there in the middle, that's a picture I drew, and this is drawn in scale. So the scale here is correct for scaling, meaning the height of the ionosphere, which is the green circle there above Earth relative to the size of the Earth. So the scale is here correct, and now you'll see how the ionosphere is actually pretty close to us. With one skip, you don't actually get that far because the ionosphere is not like way out there like it's shown on the left. Here's I know this the blue picture here is a little bit of an eye test. So here's a zoomed in version of the same thing. I just took that one section from it and zoomed in on it. So you see there's the pink ray and the red ray. the red ray or EM wave, that one takes off at an sort of theoretical 0-degree takeoff angle. So you are, I mean, ideally that's what you would do. Your signal leaves the antenna and just goes bore side to the horizon, not up at all, just smooth earth. There's no, obstructions on the way. Signal 0-degree takeoff angle, hits the ionosphere. On this drawing, by the way, I'm drawing the ionosphere at 250 kilometers. That is the, I'd say, rather typical height of the F layer that does the reflection for us. So 250 kilometers, that's the height here. So your signal takes off at 0-degree takeoff angle, hits the ionosphere at 250 kilometers, and then, air quotes, reflects down from there. If you do that truly like idea or theoretical situation here, if you do the math on that, you can reach about 2,200 miles in one skip. But that only happens in simulation or in theory. With the much more realistic, but still really good, 15-degree takeoff angle. So this is still a big antennas, a lot of aluminum in the air, tall towers, 15-degree takeoff angle. You hit the ionosphere at 250 kilometers. You cover 900 miles in one skip. That's not so far when you look at this. Like I put some example, straight line distances. San Francisco to LA, 350 miles, easy one skip. Denver already 950 miles. Denver from here is probably 2 skips most of the time. Maybe 1 skip if you're doing well, but probably 2 skips. East Coast, 2,200 miles. That's 2 or 3 skips. Most likely, probably 3. Then of course Europe, 5,000 miles. Now we're talking about 5 or 6 skips. Other side of the earth, Cape Town, South Africa, 10,000 miles, more than 10 skips. So it really highlights how efficient the HF propagation is. Our signal gets there, and it didn't do just 1 skip. It had to do 5 to 10 skips. It's pretty amazing. All right, there's always an exception. I could have left the previous slide there and not even show this, because this is sort of like exception to the previous slide, which is the normal situation. The flashlight here, by the way, illustrates the sun. I thought the flashlight looked better than just the sun. So the flashlight is the sun, radiating its light and the UV and X-rays and all that solar wind onto the Earth from the left. So the left side of the Earth here is the day side, and on the right, sort of, I guess, Europe and Africa and Atlantic. That's the night side of the Earth in this picture. What can happen? This is not the normal situation by any means, but sometimes that the solar wind and other radiation of the sun, it can really stretch out the ionosphere on the night side of the Earth. It kind of gets pulled away from the Earth. And then this situation can happen, where on the day side, the ionosphere is at its normal altitude, but on the night side of the Earth, it's much further away. And then you can have this thing happening where the signal actually bounces or reflects from the ionosphere there on the night side of the Earth more than once without ever coming back down to Earth. If you see this, I did this drawing here, and it looks kind of wonky, but it's actually geometrically correct. So all those angles work out. It's not sort of made up situation, but this kind of propagation can happen in certain situations. And when it happens, it's really great because it's very low loss propagation compared to the normal thing where the signal kind of bounces between the ionosphere down to Earth, ionosphere down to Earth. That's much more lossy. This is very low loss propagation when this happens.
Mikko?
Yep.
Is this drawing also to scale, almost might be. Is it?
Mhm. Yeah,
Brilliant.
there's the, yeah, there's it is. It is the scale. There's no like good hard numbers on how much the ionosphere can like stretch out there on the night side, but picking up some numbers I found there in the literature. This is to scale. So it again, it's not like just made to look good. This is like a real situation.
So how do you count the number of skips in this case?
Yeah, I don't know what would it be. But yeah, this thing can happen. It's not common, but it's pretty cool. And you would, at first you wouldn't even guess that's possible, that it can actually kind of ding 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 hit the ionosphere a few times without hitting the Earth anywhere in between. So, but this is the exception. It's just a kind of cool thing that I wanted to point out. All right. NVIS or NEVIS. I don't know how all you want to pronounce that. Maybe I'll call it NVIS because
We call it INVIS.
NVIS.
Yes.
Okay, I'll call it NVIS if that's what people are most used to. NVIS, so near vertical incident skywave. Pretty popular on 80 meters. You're transmitting mostly sort of close to straight up. Signal reflects back from the ionosphere. Relatively low loss, gives you reliable communication within kind of short distance. Here again, there's sort of again the geometry of the NEVIS. What did it help me again? NVIS.
INVIS.
Yeah, NVIS. So here again, the sort of the geometry of NVIS is a little bit different than what we easily sort of picture it to be. Again, this drawing is to scale. So the scale is correct. So when we talk about NVIS, if you really transmit the signal just about vertically, near vertical, if you go near vertical up and you come near vertical down, you are not getting very far. So it's definitely near vertical up and down. If you talk with somebody in Santa Cruz, if you're talking with somebody in LA, you are not actually going that near vertical anymore. Some examples here. Again, and this is really about sort of the geometry of things, like how far the ionosphere is, and what angle do you have to take off from your antenna to hit a point, at some distance where you want to talk to somebody else. So if you're going up at 75 degrees, that I consider near vertical. It's still like mostly up. If you go up at 75-degree angle, you come down at 75-degree angle, you're hitting Sacramento. That's how far you're talking to, about 80 miles away. If you're going up at 60 degrees, I wouldn't consider that near vertical anymore. But if you're going up 60 degrees, come back down at 60, you're talking to somebody at Reno, about a little bit less than 200 miles away. At 45 degrees, not near vertical anymore at all. That's what it takes to get to LA in one hop. You're going up at 45 degrees, you come back down from the ionosphere at 45 degrees. If you're talking all the way out to Portland, now you're going out at 30-degree angle. So NVIS, cool sort of propagation.
Mikko,
Yeah.
we use INVIS for emergency communications. Say we need to talk to Sacramento out of the Bay Area.
Mm-hmm. Yeah.
Then we would use this technique to do this. During the day on 40, during the night, on 80, right? So that's really what the intention is. I mean, it's not really, we don't use it for trying to get as far as we can. We actually want to see if we can localize the communication, Fresno, Sacramento, those places. But actually there was a power outage several years ago. And I was able to talk to people in LA who were affected by the power outage using INVIS. With, like you said, it was, 45 degrees or whatever. But yeah, that's really the technique we use in ecom.
Yeah. Yep. And when we get to the ionograms in a little bit here. You mentioned you would use 40 meters during the day, 80 during the night. That's an interesting topic again, to sort of revisit when we look at the ionograms. Antenna height, very sort of relevant topic with the NVIS. Sometimes people say, for NVIS, you want like really low antenna. Low antennas are the best. Well, not really. This is again one of those maybe misconception things. So on the picture there are different azimuth radiation patterns for half-wave dipole at different heights above Earth. That's what's in the picture. All the curves are for different height. Height is specified in wavelength. So for example, the pink curve there, that's the half-wave dipole radiation pattern when the dipole is 0.02 wavelengths above ground. The green one is 0.06 wavelengths above ground and going up from there. So what does that mean for example, for 80 meters? So 3.9 megahertz, one wavelength is 77 meters or 252 feet. The pink curve, the pink radiation pattern, that antenna, that 80 meter dipole would be 1.5 meters, so 5 feet, about 5 feet above ground. That is not good antenna. It's not good for NVIS. It's not, what did you call it? NVIS, yeah. It's not good for NVIS. It's not good for DX. It's not good for much of anything. If you rise it up to 8 feet, it gets better. It's the green curve there. Much more power is now going straight up. If you keep rising that dipole all the way up to 50 feet, most people would not consider that an NVIS antenna. Oh, that's high up. It's at 50 feet. It's the perfect NVIS antenna. It's still much better than any of those low dipoles. Same dipole, but lower height. So 50 feet, that is a great NVIS antenna. Only when you start to go really high up, like the red curve here, 0.4 wavelength or 100 feet, you have your 80 meter dipole at 100 feet. That is not the great NVIS antenna anymore. There you see less energy is now going straight up, more is going to the low radiation angles. This is more of a DX antenna. But for NVIS, the low antennas might work. They are not ideal. For most of us, 50 feet is pretty much as high up as we can get it. So even for NVIS, on 80 meters, it's still a good idea to get the dipole essentially as high up as you can. It's kind of surprising, but that's still how it works. Of course, for 40 meters, you can divide that in half. So for 40 meters, if you can get your antenna or get the dipole to 25 feet, you're golden. That's probably the optimum height. And I put these LA, Sacramento, Portland in this plot also, showing the sort of the takeoff angle where each of those locations is. So again, if you're talking to somebody in Sacramento, you're going up at 75 feet, and that 80 meter dipole at 50 feet, it's working great. It's the best of these. If you're talking to somebody in LA, by now you already want your dipole as high as you can. It can't be too high. Even more so if you're trying to hit Portland. Kind of interesting thing, I thought. Now we're getting into the ionograms. And really, there was a really good article in the January issue of QST. There's more information there about the ionograms than we can cram into this presentation, but let's take a look. And by the way, it's kind of funny. I started to work on the presentation before we got that QST. So when that showed up in the mail, I was like, I don't know if this is good or bad. There's basically my presentation in the QST now. And if everyone reads that, they already know everything I'm going to tell. But if they didn't go ahead and read that, I'll do my presentation and tell them, then go and read the QST. There's more information there. So what are ionograms? Ionograms are sort of plots or graphs produced by ionosonde. What's an ionosonde? Ionosonde is a test instrument. It tells us, and there are a bunch of ionosones out there in the world, owned by universities and research organizations and NOAA and organizations like that. So they own ionosones. I don't think there's a single ham out there who owns his own ionosone. So we just have to rely on the information that's there available for free online. So ionosonde, it's a test instrument that tells us how the ionosphere actually looks like right now. It doesn't give us like propagation forecast, like all those sunspot, solar flux index based propagation. They all forecasts. They all like try to make a guess what the propagation is going to be like. Ionosones measure it right now. They tell us exactly what's happening right now, and that's why it's great. So what an ionosone does and how it works is it transmits an HF signal, just like our 80, 40, 20 meter transmitters and an antenna. It transmits a signal. It transmits the signal straight up, and then it has a separate receiver. And the ionosone, it sends like a ping straight up, and then it listens for the echo, that reflected echo coming back. So that's what it does. They sweep the frequencies. They do that, send a ping, listen for the echo. They do that, typically covering the frequency range from 1 megahertz to 15 megahertz to give a good idea of what's going on within the HF bands. Of course, when you send the ping, then you receive your own signal. What they do is they measure how long did that take? How long was the delay between sending the signal and then receiving the echo of that? So the longer the round trip is up to the ionosphere and back down again, the longer it took, the higher up the reflecting layer must be. So what the ionograms show is the height of the reflecting layer. They don't talk about delay in time, but that's fundamentally what's measured is the time delay, how long that round trip took. And then the ionogram, that's a good example. That's how they look. I'm sure you actually you've seen these online or in magazines. So this is the output from the ionosonde. What's on the y-axis is the height. So from how high up did that signal go, before it got reflected back to Earth. That's the y-axis there. The x-axis is simply frequency in megahertz. So as that test is done on multiple frequencies, then that kind of fills out the graph here. And yeah, the y-axis, by the way, that's in kilometers. So let's take a look at this ionogram here as an example. I've been looking at these ionograms now kind of intently for a couple of years. There's a really nice ionogram relatively close to us in Boulder. That's where this ionogram is captured from. That's the one I often look at. Its outputs are there, freely available. I really like the format, how they provide it. So this is from Boulder, January 25th. This is a capture I took from there. So this is pretty recent. This is just from week or two ago. Let's start from the bottom. E layer. There at the bottom left, you see that those few red dots. Those are the echoes. Those are the reflections from the E layer. It gives a little bit of reflection there. Medium waves, really low end of HF. The height, that's important to note. The height of the E layer there, about 110 kilometers. Then there's those bigger red and green sort of curves. The first dip on the left, that would be the F1 layer. During the daytime, you remember we said like most of the time, sometimes you have the separate F1 and F2 layers. Sometimes they aren't. Sometimes you can't see F1 and F2 separately. In this case, they are there. They actually sort of distinct layers. So F1 layer gives that first little U, letter U-shaped curve at the height of about 220 kilometers. And then there's that much bigger, wider U-shaped kind of curve. That's from the F2 layer. A little bit higher up, 250 kilometers. And the F2 layer there is doing great job reflecting the signal straight up, straight down, reflecting them back for the frequency range of 4 to 9 megahertz. So that's straight up, straight down trip. That's your basic ionogram. The topmost red and green there that I'm pointing out, that's kind of an interesting one. That is not any layer at all. What produces that kind of cluster cloud looking collection of echoes, that's from a signal that actually made 2 round trips. That they transmitted the signal straight up, hit the ionosphere, got reflected back, hit the Earth, reflected back up again, and back down again. So that signal just did 2 round trips, and that's this cluster here. So it's not really a separate layer at all. It's sort of like a ghost thing. But what it shows is the second trip, sort of 2 round trip echoes. These are not always there. So when they are, you know the reflections are really strong. Propagation is good. So that's a good sign to have this like second cluster there. Then taking a closer look of sort of the numerical information that's provided there in the side, and not just like looking at the pretty graphs. So here on the left, they actually give a lot of numbers. They sort of interpret the ionogram for us. So here, first here at the top, there's the critical frequency, or critical frequency, or the highest frequency that's being reflected by the ionosphere when you go straight up. What's the highest frequency that still bounces back down? So for the F2 layer, in this situation at this moment would have been a little bit over 9 megahertz. The F1 layer reflects lower frequencies, 4.2 megahertz. Then you see there's the E layer. There they give 2.8 megahertz for the E layer reflection. And it's also really, that's the critical frequency, highest frequency that's being reflected when you go straight up, straight down by the ionosphere. Then there's the current height of each layer in kilometers. E layer at 110, F2 at 250, and then the F1 layer at 220 kilometers. Oops, that's a mistake. And then there at the bottom, if you look at the numbers here at the very bottom, this is interesting for us if you're trying to work DX. So these critical frequencies on the left, that's for straight up, straight down. But if you go out on a more shallow angle, then the ionosphere reflects higher frequencies. So if you look at here at the bottom, if you're trying to work real DX and you're trying to get to like 3,000 kilometers away on one skip, now the MUF, maximum usable frequencies, pretty much up to 30 megahertz. So that information is here at the bottom. Quick example, how does the ES propagation look like? Because the ES is so distinct, then the ionogram looks like this. The F layer, it's pretty much invisible, it doesn't show up, but there's a very strong, very flat reflection coming back from the E layer here. All right, well, here comes the twist. Here comes the twist. This is the fun part. nobody asked me, what's that red and green color? What does the color coding mean? It means this. The red color or the red echoes in the ionograms, they are produced by the so-called O mode or ordinary mode or ordinary wave coming back from the ionosphere. The green echoes are produced by the so-called X mode or extraordinary mode. Both modes, both waves are generated there up in the ionosphere. And this is really kind of the cool stuff. So, oops, there. Let's not jump ahead of ourselves. So, whatever polarized signal we send up to ionosphere, when that signal, let's say we transmit with the dipole, so it sends out that linear polarized, maybe a horizontal dipole, horizontal signal, horizontal, electrical field. That signal gets up to the ionosphere, and when that signal travels within the ionosphere, it gets essentially converted to two new waves, the two new signals. And these two signals that get generated there in the ionosphere, they are circularly polarized. There's two waves, there's the green and the red. And those two waves, their circular polarization rotates in opposite directions from each other. So the ordinary wave or the ordinary mode that's in red, that's right-hand polarized. The X mode, extraordinary wave, that's left-hand polarized.
Question.
Yes.
This is Rich, W6APZ. How long after this picture is taken does this exist? In other words, how long can you use the information before it changes?
Yeah, good question. Thanks for asking that. It changes fast. It's so like the Boulder ionogram, it updates every 10 minutes. And when I'm there, like watching TV and on my laptop or on my pad, and I'm like looking at the Boulder ionogram, I'm hitting the refresh button about every 10 minutes, and it keeps changing. It's not completely different from the previous every 10 minutes, but you can see it move. It changes, and you have to remember, Boulder is a little bit east of us. So what's happening in Boulder is not exactly what's happening right above us. So what's happening in Boulder is typically like hour to 2 hours sort of ahead of us, because the sun went down there already. It's still shining here. So whatever the ionosphere is doing in Boulder now, it's probably going to do around here in an hour or two. It's pretty dynamic. It's changing fast.
But if you're talking to Texas, then you want to see the from Boulder, not
Exactly.
the one above you.
Exactly.
That's another twist.
Exactly. So ideally, if you really want to sort of understand a particular link between you and the other guy, you should try to find an ionosonde online that's somewhere there between the two of you. And that ionosonde probably gives you the best picture of what's going on right then and there.
Because there's in what you said in the previous thing in the slide, I just understood something that I had never known before, which is that I just thought I'll call it out. We always say in HF in antenna polarization doesn't matter because what comes back is random polarization, and I always thought it was like sometimes this and sometimes that.
It's not.
But what you're saying is no, it's equally vertical and horizontal because it's equally circular.
Yeah, what's like that there? Like let's keep. I'll point out a couple of things about the extraordinary mode, and that's why I guess it's called the extraordinary. It actually travels a little bit slower than the ordinary mode. While in the atmosphere, the green signal, the green X mode signal, lags the red signal. It's a little bit slower. Also, it's typically a little bit more lossy, the green one. So mostly when we talk on HF, we are using the red, the ordinary wave. So that was the last thing to point out from there. And Sri, exactly true. Everyone always says, oh, the propagation is random. It gets randomized in the ionosphere. It's not random. It's not random at all. It's circular, but sort of the end result is the same. And just like you said, the signal coming back from the ionosphere that we pick up that dx or the Nevis, NVIS. The NVIS signal, very circular polarized when it comes back. You send up, you transmit it with the dipole, linear pole signal goes up, 2 rotating signals come down. Mind explode. So yeah, but because it's circular polarized signal, it doesn't matter what polarized antenna we use, because it's all the same. Just like we looked at here, this is why I had it there, the whole cross polarization signal. So if your signal is circular and you receive that with linear polarized antenna, you always lose 3 dB. But there's no right and or wrong, vertical or horizontal. It doesn't matter because the signal is circular polarized. But it's not random with what people always say. Oh, the ionosphere, the HF propagation, the signal gets like randomly polarized. It's not random. So yeah, this is the cool stuff. So yeah, the polarization of your HF receive antenna doesn't matter because the incoming signal is circular polarized. So vertical, horizontal doesn't matter. Of course, vertical and horizontal antennas have a lot of other differences. They are directional, they pick up noise in different ways. So I'm not saying that vertical antennas are equal to horizontal antennas. That's not what I'm saying. But the actual polarization of the antenna as far as picking up HF, so-called skywave signal, it doesn't matter. It's kind of an interesting thing. This is even more wild. So we have the X mode and O mode, those green and red signals that are kind of, they are made there in ionosphere. You send your signal with the dipole, linear polarized, it hits the ionosphere. What comes back down is not your signal anymore. What comes down is a new signal that was made up there. Actually, 2 new signals. And the wild thing is that the 2 new signals, they don't even travel in the same direction. They diverge as they go through the ionosphere. So the X mode and O mode diverge from each other and actually land in different places. Typically the O mode, the ordinary mode, that wave curves towards the pole, and the X mode, the green signal, that curves towards the magnetic equator. This thing usually goes unnoticed. We don't ever notice that because our HF antennas have such wide beam. They are not like a laser tight, narrow beam. If we had those, if we have a really high gain HF antennas with very, very narrow beam widths, we would see this and we would have to deal with this. You couldn't actually point your antenna towards where you think where you know the guy is, but you would have to take into account this divergent paths. But we don't have to because our HF antennas typically have really wide beam width. So this kind of goes unnoticed, but it doesn't mean that it doesn't happen. It happens every time.
Question.
So question, Mikko, what happens after the equator? I mean, I made a contact with South Africa on FT8. I was really thrilled.
Yeah.
But if one of the signals had to cross the equator, after it curves towards the equator, does it curve back? Does it keep going? What's going on there?
Yeah, no, it would start curving. So it goes towards the equator, it crosses the equator, it would actually go back towards again, back towards the equator. And then there's the special case. If you are transmitting right exactly along the magnetic equator, in that case, the X mode and the O mode waves travel straight. Yeah. Yeah.
Question.
Thanks.
Yeah, so if the, and so in the southern hemisphere, it's just the opposite in the sense it points the other direction the equator was and North Pole was.
Yeah, that is true. That is true. And I think it's on the next page where, yeah, let's jump here. So this like diverging paths. So like the RF, our transmission doesn't even travel straight. It freaking curves. That is weird. What's causing that? Short answer, it's the Earth's magnetic field. If we had the ionosphere up there, but no magnetic field, none of this stuff would happen. But since we have the ionosphere, which is, ionized gas, in the presence of the Earth's magnetic field, that's what makes all this X mode, O mode stuff happen. And that's really cool. So here's kind of an illustration. The blue chunk there, imagine that's like chunk of ionosphere, slab of ionized gas. From the left, from there comes your signal. That's what you're transmitting. Linearly polarized radio wave enters the ionized gas. At the same time, there's the vertical component of the Earth's magnetic field, and that's what we need. We need the vertical component of it. That's going through the same ionized gas, and you see what comes out from the other side. Your original, linear polarized signal, it's gone. But there are these two green and red circular polarized signal that comes out from the other side at their curved paths. And it's really that vertical component of the magnetic field that's needed here. Let me show this. So Earth's magnetic field, the normal illustration. Pay attention to the compass needle there. So at the equator, the needle points exactly north-south. In other words, the needle is parallel to the surface of the Earth. At the magnetic poles, the needle goes straight up and down, and everywhere in between, the needle is something in between being parallel to the surface of the Earth and being just pointing straight up and down. So it's that up and down part of the magnetic field, or the vertical component of the magnetic field. That's what makes these paths diverge from each other. So which means is the further north or extreme south, or the further or the closer to a magnetic pole the signal path is, the more of this diverging paths stuff happens. So supposedly, I haven't lived in Alaska, but supposedly, halves up in Alaska, they actually deal with this. So if they have very good directional HF antennas, and from Alaska, you want to talk to somebody in California, those guys, they need to turn their beam towards Hawaii, because that's where the signal is coming from, because of this like highly curved path, because up there, the magnetic field is almost exactly vertical already, and it's really causing those two signals to curve, and they're not really traveling straight anymore. So it's the inclination of the magnetic field that really plays the role here. And that's why if you are transmitting a signal right along the magnetic equator, then none of this crazy stuff happens, because the magnetic field doesn't have any up-down vertical component when you're right on the equator. Like you can see in the picture, the magnetic field lines just go straight north-south. Nothing goes straight up and down.
Hey, Mikko, quick question.
Yeah.
So in my compass, they give figures for the so-called declination angle. I've never seen figures for inclination.
No, you don't. So the declination is the sort of error, deviation between the magnetic north and the true north. So that's the declination. The compasses actually, Yeah, so there's no marking there. Sometimes there is, but most of the time you don't see a marking for inclination. But because the inclination is there, if you had a compass with say where the needle was perfectly balanced, say on a string, like here at our latitude, the inclination is about 60 degrees, and you were hanging that compass needle from a very, very light string, the needle would not point north, it would point mostly down. Why don't our normal compasses do that? Because the needle is like pre-weighted. It's not.
I have one of those. It's made by Brunton Company. I have one. Bring it here.
And our normal compasses, they are made for like sort of specific region of latitudes. If you buy a compass that's made for southern hemisphere, it doesn't work well up here in the northern hemisphere, because here in the northern hemisphere, they put more weight on the south end of the needle, so that when that vertical component of our magnetic field pulls the north end down, the company that made the compass, they made the south end of the needle heavier, so it's approximately balanced. So same way, for like polar explorers and military and stuff, those guys can buy a compass that's made for like very high latitudes, where the needle is weighted quite aggressively to sort of counteract the extreme inclination. So that's another interesting thing. Don't buy a compass from Australia and bring it up here. It wouldn't work too well.
So I want to ask the aviation folks, are there, does their backup magnetic compass on their airplanes, do they have one for different latitudes?
I don't know what they do. I don't know how they deal with that. Yeah. But the handheld compasses we have, I actually looked at I had to go and look at my compass in the garage, and sure enough, it says it's a northern mid-latitude compass. Who knew?
I need to look at my dive compass.
Yeah.
As part of my console, because I've dove in Australia and I've dove up north of so, and I've not had major issues. It's been pretty steady. When I want to do a bearing or whatever, I've not had too much of an issue.
Yeah. What happens when you use this kind of say northern hemisphere compass in the southern hemisphere, it still indicates correct, but because the needle is now, it's probably sort of like hitting the base plate or whatever, it's not balanced anymore. It's probably starting to drag a little bit, but the main problem, the problem is that it's not balanced anymore. It's the compass manufacturer, they made the south end of the needle heavier, thinking that this compass is used on the northern hemisphere, and now you brought it to southern hemisphere. So now that south end of the compass is pulled down by the magnetic field anyways, and it's also heavier. So that end of the needle is really like, it's probably going to be hitting something. So it's not going to be as sensitive anymore.
So I quickly looked up the certified flight instructors, some wiki page says there are dip compensating weights, and there is a dip correction that they do on those airplanes.
Yeah.
Actually, some company like the compass I have, that's actually an oil, it floats inside.
Yeah.
So it's not just spinning on a.
But they're still the same.
But it's floating. You know what I'm saying?
Yeah. Cool. Okay, let's wrap this up so anyway, that I'm not keeping you guys up too long. Back to Earth. Exactly. That was perfect time. So back to Earth. That was all the sort of theoretical stuff. It's what happens. It's not just a pipe dream. That's what happens in the ionosphere. But you might say, then what? Should we use circular polarization on HF? Yes, we should. We absolutely would be much better off if we did. The problem is that circular polarized antennas on HF would tend to be pretty big and unruly, so nobody does that. If we actually used circular polarized antennas, we'd get 3 dB more signal on the transmit side and on the receive side. On both ends, you would gain 3 dB because you don't have that sort of polarization mismatch where you are dealing with circular polarized signal with the linear antenna. So there's 3 dB to be gained on both ends if we use circ-pol antennas. And in many occasions, you would have much less fading. But yeah, they are just unpractical. They are unpractical except one interesting exception. I say the NVIS case, 80-meter circular polarized inverted V is actually kind of practical. It still requires just one. So there's the turnstile antenna again there. So 80-meter turnstile, still only one pole, one support pole in the middle, supports one inverted V. Add a second inverted V, at right angles from the first, feed them 90 degrees out of phase, and you are sending out beautiful, perfectly circular polarized signal straight up. This is perfect for NVIS. And it's not complicated. It requires some space, but if you have room for full-size 80-meter inverted V, maybe you have room for 2 of those at right angles from each other, and you could do this thing. And people are actually doing that. You saw already here on this bottom drawing. This one is not by me. This is by Oscar Hotel 7 Sierra Victor. His guy there in Finland, he's been experimenting with this, and he has one of these 80-meter turnstile antennas. He's using that on 80 meters, chatting with other Finns. It works great. He has an awesome signal.
Is he the guy? Is he the guy that has the huge?
No.
Oh, okay.
No, he's not that. This guy, he's sort of a little bit more of a scientist type, but he's putting his stuff into practice. So he's doing this. It's so that the center support is just one fiberglass pole, and then just 2 wire dipoles hanging from it. It's pretty simple thing. It takes a little bit of space, but the concept is super simple. So
Question?
Yeah.
Why couldn't you do the same thing with 10 meters and have a much shorter antenna?
You could. You absolutely could. Nothing wrong with that. This whole X mode, O mode thing, it tends to be more sort of stronger, more prevalent there at the lower frequencies, and it's just that sort of it's just that physical arrangement of the inverted V. You add a second one, and you're going for that NVIS straight up. That application just lends itself pretty nicely for the circular polarization. You would have the same benefit on all the bands, 10 meters, 20 meters. So if you try to make like a crossed pole beam on 20 meters, it gets big and unruly. What I realized was if anyone has a cubical quad for HF, you could make that a circular polarized antenna quite easy. You would just feed it from 2 corners, the same cubical quad. You don't need to add any more elements. You don't need to add any wire. You could just feed the quad from 2 corners, 90 degrees out of phase, and that way generate the circular polarization. So I don't know. I don't have a quad at home, but yeah, perfectly. You would get the same benefit on all the HF bands. It's just this, like the application of 80-meter NVIS with an inverted V supported by one pole it just like lends itself so easily for these circular polarization experiments. So 087SV, he's actually made this. So he's not using quarter wave coax to create the phase shift. He's using a just LC circuit, basically what is it now? Quadrature hybrid to make the phase shift. This is a board he designed. I'm building the same board. I want to give this thing a try one of these days. One last little detail you have to include when you are making, you have those two crossed dipoles, the inverted V's, you're adding this board to create the phase shift so you get the circular polarization. The one little detail you have to remember to do is you have to switch the direction of the rotation between TX and RX. You have to switch around. So you see, like on this board, one of the connectors here is PTT. So he throws a relay here based on the push to talk, so that the signal is turning one way when you transmit, and then it's turning the opposite way when you're receiving. And that's simply, just the normal sort of geometry of things. Let me turn around so that all you guys and me, we are looking in the same direction. It's going to be hard. So here I'm turning my hand in counterclockwise rotation. So let's say I'm transmitting, no, clockwise. I'm turning clockwise. Sorry, I got confused. So let's say I'm transmitting a clockwise, circular polarized signal right now, and we are pointing that way. It's turning clockwise, and now I keep turning the same way, and now you are receiving it. And from your point of view, is my finger now turning clockwise or counterclockwise? It's going counterclockwise. So if I transmit signal that turns clockwise, you have to receive it turning counterclockwise, just because you are just receiving it from the other end. Nothing, it doesn't get like flipped around in the ionosphere, like the rotation would turn the opposite way. That doesn't happen. It's simply the fact that when things turn clockwise from my angle, they turn counterclockwise from your angle. So that's why you need to switch the phase delay by 90 degrees between transmit and receive. So that's included also in this board. That's it. That's all I had.
I'm going to open it up for questions.
I have one thought, sort of in the shout out department, I guess.
Go ahead.
And thanks. And that is this phase confusion may have to do with thinking about the wave as traveling versus a standing wave. So I'm picturing in my head that a standing plane wave, the B and E would be 90 degrees out of phase. But if you think of the E wave as moving, then the peak is actually moving, and maybe that's why they're in phase. I have a suspicion that might be the way to think about that, but I'm not sure.
It's a good point. There's so many different ways and sort of different illustrations of looking at the same thing and same thing and other things that are very, very similar, that it's kind of easy to get tangled in there and get yeah.
Thanks. And great talk, by the way. Thank you so much.
Oh, thanks.
Any other questions?
So Mikko, I have a couple of trivia questions for you.
Yeah.
So I do a lot of broadcast, all this television stuff. Do you know what kind of polarization they commonly use in television broadcast? What's their common polarization?
Well, looking at aluminum on people's rooftops, you see horizontal antennas. You see horizontal.
Mostly, that's
TV.
correct.
Yes.
Well,
so
is it
the
is it
answer-
not circular but in a horizontal? You know what I mean?
Log
Actually,
antennas is what you normally see.
The answer is elliptical, because what they're doing is they put a certain amount of energy from the transmitter at the horizontal plane, and that's for the majority of the antennas that are on people's rooftops. But they also put in a vertical component because there's some people that have, like rabbit ear antennas or whatever you want to, it's like a little whip antenna kind of thing. And so for the most part, it's elliptical. Now, what about FM broadcast? What polarization do you suppose they use?
Vertical.
My FM antenna is vertical, it's horizontal.
It's circular.
Oh, it is.
If you look at the antennas here, I got to use my hands. Okay. When you look at the FM broadcast antennas, you'll see what looks like two C's like this. And they're created in a way so that it's a circular, as it radiates off the antenna pattern, it comes off spinning. They want that because of mobile, because your car FM. It's because everybody's getting signals that are bouncing off antennas. Now, everybody should know the answer to this one. What polarization is AM radio? It's a vertical. Why did they do that?
It's hard to string a dipole.
It's really hard to string a dipole at that frequency. Well, and so broadcasting it's as big a donut as you can make. They're trying to just get as far away as possible. Just thought I'd add that.
But Joel, what about that stuff by the Dunbarton Bridge? That looks.
That's
horizontal.
KGO. It's vertical. There's 3 in a row. And what they're doing is they're making essentially it's a cardioid that goes north and south.
Okay.
So they're trying to blast into the LA market and all the way up into Portland.
I thought those were horizontal because I see wires strung between the 3.
Those are just guy wires.
Oh, okay.
Then the main radiation mast is energized and they're all 3 of the KGO antennas are phased.
Okay.
So what they're doing is they're creating essentially what would look like a big figure 8 that goes mostly north and south.
Oh,
Up and down. It's to be able to cover it's to protect Fresno, but it's meant to get into LA because they're a competitive market and all that kind of stuff.
Yeah, there's 1170 LA that I hear now and then. So is it 11?
Oh yeah, you can hear KFI on a good
KFI.
night. Everybody
right.
should be able to hear KFI, which is AM 610
610.
out of LA.
Yeah.
But if you see KCBS, if you're ever up in Marin County, you'll notice that it's quad. They have a square pattern, but they have this phasing array thing that they do. They also do a little RF, whatever that phasing harness thing is that they've got. But so anyway, everybody's trying to do the same thing. They're trying to saturate the market that they're trying to get into.
Hey, Joel, a question.
Sure.
So I understand in the UK, their TV antennas are vertical, but maybe they do this elliptical trick on it also, do you know?
Well, most of their frequencies are UHF. Andy, they don't have VHF like we do. So their antennas are optimized for the band that they have. And all the bands in Europe are UHF. They don't have VHF.
Yeah, I think in movies I've seen also in Italy and other places where they appear vertical.
You'll see bow ties. You'll see, those really optimized Yagi antennas and stuff like that are, small, compact, whatever. But yeah, they don't have VHF in Europe, or not in England, that is.
There is one peculiarity in France, close to the mountainous regions, where they use antennas with the circular polarization for television. I forget the exact detail, but there are peculiar antennas in the mountainous regions in France.
Yeah, they're also elliptical. So most TV broadcast guys they're no different than anywhere else. So they've optimized to be able to get the broadest amount of viewership capability kind of thing. And with digital, elliptical is more conducive for getting a good solid signal.
And Mikko, once again, thank you. I think as technical it was, everybody was kind of impressed with some of those graphs and some of the things that came up there. So thank you very much.